All right. Let's start. All right. Welcome back. Let's move forward in our journey through NP, P, NP completeness, and things like that. Okay. So let me recap quickly what's happened in the last couple of lectures. Firstly, we have two classes of problems. NP, these are problems for which you can verify the solution. P, problems for which you can find the solution. And then there's this big question whether NP is equal to P, meaning whenever you can verify a solution, can you also efficiently find the solution? Okay, so that's the setup. So you have two problem classes, NP and P. Okay, and we saw lots of problems fall into this class NP. In particular, the entire class of polynomial time solvable problems, which is P, fits inside NP. And then we have other problems, factorization and three coloring and so on. Okay, and then the next thing we did is we want to compare the difficulty of problems in NP or elsewhere. So to do that, we defined this notion of reductions. It's a very natural notion. We say that a problem A reduces to problem B in polynomial time if you can use an algorithm for problem B to solve problem A. Okay? So that's the key definition you want to remember. If you can use an algorithm to solve problem B as a black box to solve problem A, that is A reduces to B. And we denote it by this symbol, A less than or equal to B. And in fact, it sort of means A less than or equal to B in that if you have a reduction from A to B, then B is a harder problem. It's formally a more difficult problem than A. Okay, so that's reductions. And once we have reductions, we can now start reducing between problems within NP. We can look at the various problems in NP and start constructing reductions between them. And it turns out that something neat happens is that there's a class of problems called NP complete problems, which I've shaded in the yellow there. These are problems like three coloring, Hamiltonian cycle. These are problems that are harder than every problem within NP, meaning every other problem inside the class NP reduces to any of these. So any problem for which you can verify the solution can be reduced in polynomial time to one of the NP complete problems, like three coloring or Hamiltonian cycle. And by definition, this also means that the NP complete problems reduce to each other. So we have a class of NP complete problems. These are problems which are the hardest problems in NP, which are all of equal complexity. And if any of them becomes solvable in P, then the entire class NP collapses to P, and you'd have NP equal to P. Okay? And that's where we were. Today we'll see a couple of reductions and NP completeness reductions. Before we do that, any questions sort of that I can answer? Yes. Okay, the question is, what is the difference between NP complete and NP hard? So it's a great question. I should make sure I have the notations right here. When I say this definition for NP complete needs to say a problem A in NP is NP complete if everything else reduces to it. So, okay, what is NP hard? NP hard is basically just means harder than every problem in NP. Right, meaning every problem in NP reduces to it. So, for example, the halting problem, which you cannot solve, is an NP hard problem. Because if you treated this picture as increasing computational complexity as you go up if the difficulty of the problem increases this way, you can think of NP hard as anything that's above everything in NP. Like something like halting is not at all solvable, right? It's right up there. Or counting solutions to some, counting the number of colorings. These are all problems which are NP hard, in that they are harder than everything in NP, but not just that, they are not even in NP. You can't even verify the solution, right? On the other hand, NP complete means that it's inside NP, but it's harder than everything. So it's literally the top sliver of this little box I've drawn. Right? If in terms of difficulty, it has to be at the top edge. It's inside NP, but harder than everything. So it's the top edge of this class that I've drawn. Yes?
When we talk about NP problems being verifiable and P problems being solvable, if we can verify the solution of the problem, haven't we already found it? Like, haven't we already sort of found it yet?
So the question was about the definition of NP and P. So let me repeat this definition again. It's very important. All of you should get this. NP is the class of problems for which if you're given the input and the solution, if somebody gave it to you, then you can verify the solution. Okay? So I'm assuming that you give the input and the solution, then you can then you need to be able to verify it efficiently. P is the class of problems for which if you're just given the input, you can find the solution. Okay? Just like this is the difference between grading a homework versus coming up with a solution for the homework. Right? Grading a homework, somebody hands you the question and the solution, you just need to verify it. Right? That's easier than solving the homework, where you see the question and you solve. Right? Okay, so, all right, so let's go further. All right, so today we'll see reductions. In particular, the thing that we'll see today is that the circuit SAT problem is NP complete. This is the first reduction I'll show, the first theorem I'll show. This is, you could say, this is the mother of all NP completeness results, in the following sense that this is the first problem that we'll prove is NP complete. Okay? But let's not get ahead of ourselves. Let's just understand what the theorem is saying. It's saying that this particular problem, circuit SAT, is harder than every problem in NP. Okay? And what is a circuit SAT problem? Well, it's just the following thing. You're given a Boolean circuit, which has ANDs and ORs and NOTs gates. You want to find some assignment to the inputs so that the output is 1. Okay? You should check that this is a problem in NP, meaning if I tell you the solution, you can easily verify that it's a solution. So it's a problem in NP, and we'll see now that it's NP complete. Okay? So the input is a circuit. You want to find the inputs so that the output is 1. Okay, that's the circuit SAT problem. All right, so now I want to prove that the circuit SAT problem is NP complete. Sorry. Okay, so if I have to prove that it's NP complete, by definition I need to prove two things. The first thing is easy. You need to prove that it's in NP. Okay? So I'll leave this for you to convince yourself that this is true. Okay? Convince yourself. Okay, so that's the first thing. Okay, but the more important thing and the more interesting thing is I need to prove that circuit SAT is NP complete, meaning for every problem, take any problem A that is inside NP, it should be the case that A reduces to circuit SAT. So I need to give you a reduction from any problem in NP to circuit SAT. Okay, that's the plan. I'll show you this reduction, but to keep things concrete, let's just pick A to be some nice problem we understand very well, right? But eventually we'll see that this works. The reduction, the proof works for any problem. For now, let's just say fix A to be the factorization problem. Okay, what is the factorization problem? It's this. So the factorization problem is this very simple problem in NP. I just give you an n-bit integer. That's the input. And the solution is 2 factors which multiply to n. So 2 numbers p and q such that p times q is n. Okay? You can verify this computation by just multiplying the numbers and checking that the output is n. This is a problem in NP. And this is going to be, just the example we'll use now. And so now I'll try to prove to you that factorization reduces in polynomial time to circuit SAT. Okay? Okay? What that means is if you have an algorithm to solve circuit SAT, then you can use that algorithm to solve factorization. If you have an algorithm to solve circuit SAT, you can use that algorithm to factor numbers. Okay? That is what we are trying to prove. All right, so we have to construct a reduction. Okay? By reduction, what we mean, we have let me draw a black box. So this is a black box that is an algorithm for circuit SAT. So what does it take as input? It takes a circuit as input. It can take a circuit as input. And it will either output a solution X or it will say no solution. Okay? That's what we have. We have an algorithm to solve circuit SAT. Now we want to use this to solve factoring. So what do we have for factoring? Well, we have a number. We have a number, like an n-bit number that we want to factor. Okay? We want to use this to do that. This algorithm only takes circuits inside. I can't feed in a number. So I need to take this number and make it into a circuit. So where am I going to get this circuit from? Well, let's see. So firstly, factorization is in NP, right? Meaning it has a verification algorithm. So factorization is in NP. It has a verification algorithm. What is a verification algorithm going to be? Well, it's just going to be the following simple thing. You get the input, which is the number n, and then you get the solution, which are two numbers p and q. Okay? And what is the verification algorithm going to do? It's going to, I'm going to draw it like a, so it's going to multiply p and q. Okay? I'm just talking about how you verify a solution to this. So if you take p and q, you multiply it, and then you check if the answer is equal to n. Okay? So that's how a verification algorithm for factorization looks like. Okay? I've drawn it not like an algorithm, but I've drawn it like a circuit because we're not going towards making circuits. So, in fact, let's not think of this as an algorithm. Let's think of it as a circuit. After all algorithms can be implemented in circuits. That's, I'm going to just claim it for now. But in this case, actually, it should be even more clear because we do have multiplication circuits. Right? That's what is there in your processor. And I mean, you might even have seen a multiplication circuit diagram or something. But basically, this is a circuit. Right? What does a circuit do? It takes n, the input, and a solution to factorization and verifies it. Okay? Okay, so let me take this circuit. Let me take this circuit. I'm trying to see if I can. Okay, this is a circuit. It seems to have three inputs, n, p, and q, and it outputs 0 or 1. It's like the verification circuit for factorization. This is a verifying circuit. Okay? Good. And it outputs 0 or 1 based on whether the check passes through. Okay. So now, so that's just for factorization. So now we seem to have a circuit. So we sort of know what to do now. So let's see. So I have a number n that I want to factor. Right? This is some number n that I want to factor. Okay? I want to convert it into a circuit. Right? What's the circuit I'm going to set up? Well, it's just going to be right. So the circuit I'm going to feed in would be the verification circuit. Right? We have a verification circuit that verifies that the answer is right, that verifies that factorization is right. You look at the verification circuit, it had 3 inputs, right? It had N, P, and Q. It had like an N-bit input, N, and this is N, like I should use, it had an N-bit N, and then it had some other inputs which correspond to P and Q. Okay, that's the verification circuit. Now what I'm going to do is I'm going to take the verification circuit, I'm going to hard code N in here. I'm going to fix these inputs to N. I can always do that, right? I can take a circuit and pick any subset of inputs, set them to 0 or 1, whatever, and still have a circuit, right? It's just what it is, right? So I take the verification circuit for factorization, fix the input N to N, like, I fix the, now I have this circuit where N is fixed, P and Q are not fixed, right? These wires are not fixed. Okay, and what is factorization? Factorization is give me some values of P and Q that will make this verification pass through, right? And that's what algorithm for circuit SAT will do. The algorithm for circuit SAT, if you give it a circuit, it will give you inputs that will make the output be 1. So you send this verification circuit to the algorithm for circuit SAT. It will find an assignment of inputs that will make the output be 1. In this case, it will find P and Q that makes the output be 1. Yes, question. Why can't exponential time algorithms be? Right. Okay, it's a great question. The question was, where are we using the fact that the verification for factorization is an easy thing to do? We should use that because that is the only thing we know about factorization. It's a problem in NP, meaning verification is easy. So I should use that here. The place where I'm using it is when I construct this circuit for verification. The size of that is basically proportional to the runtime of your verification algorithm. If you have an algorithm that takes n steps, when you convert it into a circuit, it will have maybe n gates. Right? And so this circuit the size of this circuit will be basically the size of the verification algorithm. In this case, it's the size of multiplication gates and the multiplication and equality. And that is going to be some polynomial in the input size, which is n bits. Any questions? Don't be too alarmed if you don't get this immediately. This is the this is the most powerful reduction that we do, but also the most subtle. So because you're not dealing with objects that you normally encounter, like graphs or Boolean formulae. You're taking an algorithm and giving it another algorithm as input. You're taking this algorithm for circuit SAT, which takes a circuit as input, and you're giving it this multiplication circuit. Oh, look, this is a verification procedure. Now you tell me how to satisfy this. You'll tell us how to satisfy that, and it'll give us the inputs P and Q. right? So that's why it's a little bit subtle, but don't be alarmed. The reductions that come will be dealing with more concrete objects. But this is a very, very powerful thing, because what we're seeing right now is I didn't use anything about the problem factorization. I could do this proof for any problem in NP. Take any problem in NP, take its verification procedure, make that into a circuit, and give that to circuit SAT and say, what should I feed in so that the answer is 1? And that circuit SAT will solve that for you. And therefore, any problem in NP can be solved just because you can encode all algorithms by circuits. Okay? And that's basically the idea. It's an extremely powerful thing because we got our first NP complete problem, and we basically reduce every problem in NP to circuit SAT. Okay? Question? Okay, the question was what is defined as a circuit, right? So the thing I defined as, when I defined circuit SAT, is a circuit SAT takes a circuit with just 2-bit OR gates and 2-bit AND gates. Okay? The thing that I pushed under the rug is how do you take an algorithm like multiplication and write it out in terms of AND gates and OR gates and so on. You just have to trust me, you can do it, and it's sort of a mechanical thing. But that you can take any algorithm and distill it down to a circuit with AND gates, OR gates, and NOT gates, and the size of the circuit will be proportional to the runtime of your algorithm. Yes?
For the circuit, the verified circuit factorization, why does it not assume what the bit lengths of P and Q are going to be?
Right. So, so the question is about the bit length of P and Q, which are inputs to this verification circuit. Yeah, you have to be a bit more careful when you write out the details of the verification algorithm. In this case, it's not too important, but if you had to do it, you'd have to say, okay, you have a multiplier circuit that takes 2 n-bit numbers and produces a 2 n-bit number, and then you have an n, capital N, which is an n-bit number. Then you check equality with the last n bits. And so but basically, any verification algorithm, the key high-level abstraction is any program that runs for, let's say, t steps, you can distill it down to a circuit with roughly t squared gates. Okay? Or let's not, but just some small number of gates. And so satisfying any verification procedure is the same as satisfying a circuit. And so solving any problem in NP is the same as solving circuit SAT. Okay? That's basically it. It's a very simple idea, but it's very powerful. Okay, so any questions at this point? Okay, so let's move on from this. So this is our first NP complete problem. So we have circuit SAT is NP complete. And then what we'll do now is we will actually start doing reductions from circuit SAT and see that many other problems are also NP complete. Okay, so let me define. So this is the 3-SAT problem. So the 3-SAT problem, the input is a 3-SAT formula on variables x1 through xn. It's Boolean variables. So the formula looks like so. It's a formula that you've seen 2-SAT, so 3-SAT looks very similar. So it's like x1 or x2 or x3. This is a clause. So you can have a clause like this, and so this is and, not some x4 or not x5 or x6 and xi or not xi or xj or xk. So you have basically a 3-SAT formula looks like you have n Boolean variables and you have m clauses on these Boolean variables. These are like constraints, right? So think of it as there are m constraints on n Boolean variables. So this is a formula with, let's say, M clauses. Right, so M clauses are C1 through Cm. I'll just use each clause is like a OR of three things. Each clause is an OR of three things. So it's basically some sort of constraint satisfaction problem where the constraints are of a special type. Every constraint looks like x1 or xi or not xj, and so on and so forth. Okay, that's the input. And as you can imagine, the goal is to find a satisfying assignment. Find, or goal, or the solution, as we used to call it, solution is an assignment that satisfies all the clauses. Some assignment like x1 to 0, x2 to something, some Boolean assignment that satisfies all the clauses. Okay? We have seen 2SAT I think we saw it on the homework, but this is 3SAT. You have three variables per clause. And let's assume that these variables don't have to be distinct. So you could repeat the variable in a clause for now. Let's just say it could be x1 or x1 or x2, right? Let's just, okay? So that's the 3SAT formula, 3SAT problem. And you can see that there's the naive algorithm takes 2 to the n time. You try every possible assignment, see if it satisfies all the clauses. You can also see it's an NP problem. If I give you the assignment, you can just check that it satisfies all the clauses. So it's an NP problem. So, okay. And first thing we'll prove now is 3SAT is NP complete. Okay? So I want to prove that 3SAT is NP complete. So in order to prove that 3SAT is NP complete, what I'll do is I'll take a problem that I know is NP complete and reduce it to it. I know circuit SAT is NP complete. We just saw the proof. So I'll reduce circuit SAT to 3SAT. Okay? Okay, so this is what we want to prove now, that circuit SAT reduces to 3SAT. All right? Okay. Okay, let's see how this goes. So again, when you reduce circuit SAT to 3SAT, all you're trying to do is you have an algorithm to solve 3SAT. You're using it to solve circuit SAT. So we have an algorithm to solve 3SAT, and we want to solve circuit SAT. So we have a circuit. So I've drawn this circuit here. We have a circuit here. See? And what we want to do is we want to somehow transform it into a Boolean formula or a 3SAT formula. That we can feed to our mythical black box 3SAT algorithm. Right? So we want to understand how to convert the circuit into a 3SAT formula. Okay? So far everyone is with me? Okay, so now, so I need to construct this 3SAT formula. I need to decide what are the variables of my formula. Okay? Okay, what are the variables? Well, the variables are, of course, going to be the inputs of the circuit. So the variables of my formula will be the inputs, x1, x2, xn. Okay? I have my circuit, I've got the variables in. But I think I need more variables. In particular, for every wire in the circuit, I'm going to have a variable. Every wire in the circuit is going to be 0 or 1. It's going to be Boolean. So I need to have a variable for it. So I just have one variable for every wire in the circuit. So the variables will be x1 union xn. These are the inputs. And I'll call this w1 through wm. These are the wires, the internal wires. Okay? Okay, so we know what the variables are. So now what do we want to do? We want to convert the gates into the clauses, right? We want to convert the gates of this circuit into clauses so that if you find a solution satisfying the clauses, that looks like valid computation on the circuit, right? What you want is that if you find an assignment satisfying this formula, it should give you an assignment that makes the circuit output 1. Right? Okay. So let's see how to do that. Let's try to do that gate by gate. Okay? So let's say in the circuit you have a AND gate. And then let's say the input is a wire WI, and then this is another wire WJ, and the output is a wire WK. Okay? The constraint between the values on these wires is that WK must be equal to WI and WJ. Right? This is if you had to write constraints, you would love to write constraints like this. If I write a constraint like WK is WI and WJ, that really expresses the fact that there's an AND gate between these wires. Right? But I can't really do that because I'm only allowed to write clauses. 3-sat formula can only have clauses. So I just need to figure out a way to make this into clauses. Okay? Or write clauses that achieve the same effect as having this constraint. Okay, and I'll show you how to do that. But it's not the details of how I do that. It's not super important for the bigger picture. Basically, the thing to remember is any constraint on 3 variables can be expressed in terms of clauses. Okay, in terms of at most 8 clauses. Any constraint on 3 variables. And this is some Boolean constraint on 3 variables. You can express it in terms of clauses, and we'll do that. But the details are not important. But if you want to know the details, I'm just going to tell you anyway. So basically, what are the forbidden assignments? Well, these are the forbidden assignments. Let me say. So what are the forbidden assignments to this? Well, 1, 0, 1, 0, 1, 1, 0, 0, 1, and 1, 1, 0. Okay? These are the things that you should not have. Right? These are the 4 assignments at which WK is not equal to WI and WJ. Right? So that tells you what sort of constraints you should add. This says that you should have WI, not WI, or WJ, or not WK, and this is WI, or not WJ, or not WK, and WI or WJ or not WK and not WI or not WJ or WK. Okay? So if you tuned out for the last 4 minutes, don't worry. Basically all I'm saying is these 4 clauses encode that constraint. Okay? And you can do this for every gate. If you have an OR gate, it will be somewhat different. If you have a NOT gate, it will be somewhat different. But basically, you can encode any gate on 3 variables using clauses. All right? And that's what we'll do. We have our formula. We have decided the variables and of the formula, which are all the inputs and all the wires. Okay? And we just want Okay, now I need to tell you what the constraints are. The constraints are basically encode each gate. Encode each gate of the circuit, right? By just doing what I said, right? If it's an AND gate, you do this. If it's an OR gate, you do something different, and so on. But it's just encode all this. Okay? And then finally, you also have to encode one more constraint. What is that? Yes. Yeah, the output of this circuit has to be 1, right? Our goal is to find an assignment so that the output is 1, right? So let's say the output wire, we have names for all the wires. Let's say the output wire is WM. You would want to encode the constraint that WM is 1. So you could add a clause like WM or WM or WM. Okay? Okay, so that gives us the construction of the formula from the circuit, and you can see that the construction is very efficient. You can basically do it in polynomial time. You just have to go over every gate. For every gate, you add 4 clauses or 3 clauses or something, and then you have a bunch of clauses on a bunch of variables. So you converted the circuit into a bunch of clauses on a bunch of variables. Okay? Any questions on this so far? All right. Yes.
The encoding of the gates, how does that? What kind of intuition can I have? Encoding the other side.
The encoding of this. The question was, how did we come up with this encoding of the gates? Basically, every clause precludes one assignment, and you have to preclude those 4 assignments. But another way it says you just it is some easy fact about Boolean function 3 variables that you can encode all of them using these clauses. So let's not try to prove it now. But there are many ways to see that can do this. Yeah. Okay. Good. All right, so so let's let me say one more thing. To say that to complete the proof that 3-SAT is NP complete, to prove that, we need to show the following things. Okay, if the circuit C has an assignment, you have a solution to the circuit C such that C of x is 1, then there exists a satisfying assignment to the 3-SAT formula that you constructed. Okay. This is, in this case, the proof is very easy because our construction is very straightforward. We are just saying if you have a satisfying assignment, the inputs are going to be x1 through xn. The values of the wires are going to be the assignments to w1 to wm. So really, the constraints of the formula encode the gates. So it's clear that a valid computation of the circuit will give you a valid assignment of 3-SAT formula. And the converse is also pretty easy to check. The converse we need to check is given a satisfying assignment to formula, you want to say that we can find a satisfying assignment to circuit. Well, that's easy because you can just use the assignment to the x variables. An assignment to the formula will have assignments to x's and w's. You just use the assignment to the X variables as your input to the circuit. Everything will be fine because the constraints really encode the gate-by-gate computation of the circuit. Okay, good. So that's the proof that 3-SAT is NP-complete. All right, so okay, so all right, so I'm just wondering if I should do this reduction now or should postpone it. Okay, let's try. Okay, so let me define this problem. So what is happening right now is we got one problem to be NP-complete, which is circuit SAT, and then it sort of cascades. Once you have one problem is NP-complete, you find reductions to other problems, and you'll have a whole array of problems that are NP-complete. So we started from factorization today, and we've ended up at circuit SAT, now at 3-SAT. Now we can actually go to a graph problem. So if your whole trajectory, you reduced factorization to a graph problem, right? So that's what happens. So, okay, so let's look at the independent set problem. Okay, what is the independent set problem? It's just the following problem. You have a graph. Okay, you have a graph, and your input is a graph, and a number k. Okay, you want to find a subset of k vertices that don't have any edges on them. Okay, so if you think of this as an acquaintance graph, you want to find k people who are complete strangers to each other. Okay, you're given a network of acquaintances, and to find k people who are complete strangers to each other. Right, that's the independent set problem. So there is no edges between the k vertices. So that's so you're given the graph and the integer k. Okay, so now let's see how to reduce from 3-SAT to independent SAT. Okay, the reduction is going to be the following. So what do we need to do? We have this 3-SAT formula. I just wrote down something here. I want to convert it into a graph. Okay, so here's what I'll do. For every clause, I will create a triangle. So I'll create a triangle for the first clause. I'll create another triangle for the second one. Okay, so what does a triangle enforce? If you have a triangle in an independent set, I can only pick one of them, right? So I can only pick one of the three vertices in any triangle. If I pick two, they won't be independent. They'll be connected by an edge. Okay? Okay. So that's good. And somehow the thing I'm going for is the following. If I have a satisfying assignment, let's look at a satisfying assignment to these variables. So let's say x equal to 1, y equal to 0, z equal to 0, w equal to 1, and t equal to 0. Some satisfying assignment. Okay? What's happening is if you look at a satisfying assignment, it picks up at least one vertex at every clause. In every clause, there'll be one of the three variables will be 1, right? That's a satisfying assignment. So in x or y or z, x is 1. In not y or not z or w, I guess y is 1, not y is 1, not z is 1, and so on. Okay? So that's good. So my intent is that you pick an independent set where you pick one vertex from each of these triangles. That's my intent, right? So what I want you to, when you're coming up with a reduction, you're sort of encoding solutions to one of the problems as solutions to the other, right? So you want to be saying that, you're satisfying the first clause. How are you satisfying the first clause? Well, because you have x is 1. So it's probably you should do this. Okay? How are you satisfying the second clause? Well, these two are 1. So you should maybe do this. And how are you satisfying the third clause? Well, w is 0, x is 1, and t is 0. Okay? So this is the thought process behind coming up with a reduction. I'm trying to encode solutions of one into solutions to the other. Now, this looks like an independent set because you see that I picked one from each triangle. They're not connected to each other. Everything's fine. So this is an independent set. Okay? So a solution seems to go to an independent set. That is good. However, I should not be allowed to pick y and not y. Right? I should not be allowed to pick out y in one clause and not y in a different clause. That amounts to saying I'm setting y equal to 1 here and y equal to 0 there. Right? We don't get to do that for 3-sat. So therefore, I need to enforce that constraint. So I'm going to add more edges to my graph. Okay, I'm going to connect y to not y. Okay? That enforces that I can't really pick both. Okay, so now let's see. There are z to not z. Okay, w to not w. Are there any other edges? There's no other edges. So this is my graph now. My graph is this triangles for every clause. And then if I have two literals, x and not x, in two different places, I'm just going to add an edge between them, saying you can't pick both. Okay? So now that's how that's how you can design a reduction. Basically, what you do is you try to make sure that the solutions to one problem are solutions to the other. We sort of started doing that. And then we wanted to make sure that there are no spurious solutions in the second problem. Meaning, you should not be allowed to pick x and not x in the graph, because you can't do that over there. So that's why you add more constraints on the right. I added these blue edges so that you can't pick y and not y. You have to pick only one of them. And so that's how you come up with the reduction. So, but that's just, all of this was how you come up with the reduction. The proof of the reduction is just going to be two facts. We have to prove that if you have a satisfying assignment, you get an independent set. And if you have an independent set, you get a satisfying assignment. That's what you need to prove. Okay, so I think I'll do the proof of the reduction in the next class. Any questions? Okay, yes.
We have one satisfying assignment, then the assignment given from this reduction is not necessarily the one, right?
Yes. Yeah. All right, so let's complete this in the next class.